The statement in example D3 of Annex D of the 2005 National Electrical Code, under the heading Feeder Neutral Conductor, does indeed imply that when sizing the neutral for a feeder that supplies a lighting load in a building where 210.11b does not apply, the entire lighting load must be considered as the maximum imbalance. This is because, in such buildings, there is no requirement for the lighting load to be evenly distributed. However, it is important to note that this statement is only applicable to the specific example in Annex D3. The general rule for sizing the neutral conductor for lighting loads is still found in 210.19a, which states that the neutral conductor shall be sized to carry the maximum imbalance of the load. In most cases, the maximum imbalance of the lighting load can be assumed to be 70% of the total lighting load. This is based on the assumption that the lighting load will be evenly distributed throughout the building. However, in buildings where 210.11b does not apply, this assumption cannot be made. In such cases, the entire lighting load must be considered as the maximum imbalance. As for the examples in Annex D, it is true that they all use the entire lighting load as the maximum imbalance, even those that are computed on the basis of volt-amperes per square foot. This is because the examples in Annex D are intended to illustrate the application of the general rules in Article 210. In these examples, the lighting load is assumed to be evenly distributed throughout the building. However, this assumption is not always valid in practice. In conclusion, when sizing the neutral conductor for a feeder that supplies a lighting load in a building where 210.11b does not apply, the entire lighting load must be considered as the maximum imbalance. This is because, in such buildings, there is no requirement for the lighting load to be evenly distributed. Let's break this down further. Firstly, understand the context of Annex D. Annex D in the National Electrical Code provides examples of how to perform load calculations. These examples are intended to be illustrative, guiding users in applying the code's requirements to real-world scenarios. Example D3 specifically addresses feeder neutral conductor sizing, which is a crucial aspect of electrical system design. Secondly, consider the significance of 210.11b. Section 210.11b deals with branch circuits for dwelling units. It mandates that branch circuit load calculations consider the load to be evenly distributed among the circuits. However, this requirement does not extend to all building types. In buildings where 210.11b is not applicable, there's no obligation to ensure an even distribution of the lighting load. Thirdly, grasp the concept of maximum imbalance. The maximum imbalance refers to the largest possible difference in current between the neutral conductor and any one of the phase conductors. When sizing the neutral conductor, you must account for this potential imbalance to prevent overloading and ensure safe operation. In buildings where lighting loads may not be evenly distributed, the maximum imbalance could be significantly higher than in situations where even distribution is enforced. Fourthly, the 70% rule is an assumption. The assumption that the maximum imbalance of the lighting load is 70% of the total load stems from the idea that lighting fixtures will be reasonably spread out, thus mitigating significant current imbalances. However, this assumption is invalidated when 210.11b doesn't apply, as there's no guarantee of even distribution. Fifthly, the VA per square foot method is another important factor. Even when calculating the lighting load based on volt-amperes per square foot, as is common in commercial buildings, you must still consider the potential for uneven distribution if 210.11b is not in effect. The volt-amperes per square foot method provides an estimate of the total lighting load but doesn't inherently guarantee balance across phases. Sixthly, to illustrate an example, imagine a warehouse where all the lighting is concentrated on one side of the building. In this scenario, even if the overall volt-amperes per square foot calculation seems reasonable, the actual current flow in the neutral conductor could be much higher due to the concentrated load. In such cases, you'd need to treat the entire lighting load as the maximum imbalance when sizing the neutral conductor. Seventhly, regarding practical implications, the correct sizing of the neutral conductor is critical for safety and reliability. An undersized neutral conductor can overheat, leading to insulation damage, fire hazards, and system malfunctions. By considering the potential for maximum imbalance, you ensure that the neutral conductor can safely handle the anticipated current flow. Eighthly, for application of these concepts, when designing electrical systems for buildings, the first step is to determine whether 210.11b applies. If it doesn't, you must carefully evaluate the potential for uneven lighting load distribution. If there's a possibility of significant imbalance, it's prudent to size the neutral conductor based on the entire lighting load, rather than relying on the 70% assumption. Ninthly, another important factor is coordination with other codes. The National Electrical Code works in conjunction with other building codes and standards. It's essential to ensure that the electrical design aligns with all applicable regulations, including those related to energy efficiency and safety. Tenthly, always consult with qualified professionals. Electrical system design is a complex field that requires expertise and experience. It's always advisable to consult with qualified electrical engineers and contractors to ensure that the design meets all applicable codes and standards and provides for safe and reliable operation. 11thly, in summary, understanding the nuances of neutral conductor sizing, particularly in situations where lighting loads may not be evenly distributed, is crucial for ensuring electrical system safety and reliability. By considering the potential for maximum imbalance and applying the appropriate code requirements, you can design electrical systems that meet the demands of various building types and applications. The discussion about sizing neutral conductors for lighting loads, particularly when 210.11b doesn't apply, often leads to questions about harmonic currents. Let's expand on the topic by considering how harmonic currents affect neutral conductor sizing. Firstly, harmonic currents are multiples of the fundamental frequency, which is typically 60 Hz in the United States. These currents are generated by nonlinear loads such as electronic devices, computers, and some types of lighting, including LED and compact fluorescent lamps. Secondly, unlike fundamental frequency currents, harmonic currents can act arithmetically in the neutral conductor in a three-phase system. This means that the neutral conductor can carry more current than any of the phase conductors, which can lead to overheating and other problems if the neutral conductor is not properly sized. Thirdly, the third harmonic is particularly problematic. Odd harmonics, such as the third, fifth, and seventh, are more likely to be present in significant amounts in three-phase systems. The third harmonic, in particular, is a triple harmonic, meaning it is 3 times the fundamental frequency, or 180 Hz. Fourthly, the effect of triplet harmonics, which include the third and its multiples 9th, 15th, etc., is that they do not cancel out in the neutral conductor in a balanced three-phase system. Instead, they add together, potentially creating a large current in the neutral. Fifthly, regarding sizing neutral conductors for harmonic currents, the National Electrical Code requires that the neutral conductor be sized to carry the maximum neutral current. This means that the neutral conductor must be sized to carry not only the unbalanced load but also any harmonic currents that may be present. Sixthly, there are several methods for determining the harmonic current content of a load. One method is to measure the current with a harmonic analyzer. This is the most accurate method, but it is also the most expensive. Another method is to estimate the harmonic current content based on the type of load. For example, electronic devices typically have a high harmonic current content, while incandescent lighting has a low harmonic current content. Seventhly, when estimating harmonic current content, it is important to be conservative. It is better to overestimate the harmonic current content than to underestimate it. This will ensure that the neutral conductor is adequately sized. Eighthly, in some cases, it may be necessary to use an oversized neutral conductor to accommodate harmonic current. For example, if the harmonic current content of the load is high, it may be necessary to use a neutral conductor that is larger than the phase conductors. Ninthly, to mitigate harmonic currents, there are several ways to reduce harmonic currents. One way is to use harmonic filters. Harmonic filters are devices that are designed to block harmonic currents. Another way is to use power factor correction capacitors. Power factor correction capacitors can reduce harmonic currents by improving the power factor of the load. Tenthly, the selection of appropriate equipment to handle harmonic currents is important. When selecting electrical equipment, such as transformers and generators, it is important to choose equipment that is designed to handle harmonic currents. Equipment that is not designed to handle harmonic currents can overheat and fail. 11thly, in summary, harmonic currents can have a significant impact on neutral conductor sizing. It is important to consider harmonic currents when sizing neutral conductors to ensure that the neutral conductor is adequately sized to carry the maximum neutral current. The NEC provides guidance on sizing neutral conductors, particularly in sections 220.61 and 310.15. These sections address neutral conductor sizing for various types of load, including those with harmonic currents. Let's delve deeper into these aspects, focusing on the practical implications for different scenarios. Firstly, understanding 220.61, Section 220.61 of the National Electrical Code provides guidance on calculating the neutral load for feeders and services. It outlines how to determine the maximum unbalanced load, which is a key factor in sizing the neutral conductor. The calculations involve considering the type of loads connected, such as lighting, receptacles, and appliances, and applying demand factors where appropriate. Secondly, understanding 310.15, Section 310.15 details the allowable ampacities of insulated conductors. It provides tables and guidelines for determining the maximum current carrying capacity of conductors based on factors such as conductor size, insulation type, ambient temperature, and the number of conductors in a raceway or cable. This section is crucial for ensuring that the selected conductor size is adequate for the calculated neutral load. Thirdly, application of demand factors is something to be aware of. Demand factors are multipliers applied to the connected load to account for the fact that not all loads will be operating at their maximum rated current simultaneously. The National Electrical Code allows the use of demand factors in certain situations, which can reduce the calculated neutral load and allow for a smaller neutral conductor size. Fourthly, when dealing with nonlinear loads and harmonic currents, it is important to consider the impact of these currents on the neutral conductor. As previously discussed, harmonic currents can add arithmetically in the neutral, potentially increasing the current flow significantly. In such cases, the neutral conductor may need to be oversized to accommodate the harmonic current. Fifthly, in existing installations, assessing existing installations can involve measuring the neutral current using an ammeter or clamp-on meter to determine the actual current flow. This can help identify situations where the neutral conductor is overloaded or undersized. Sixthly, regarding voltage drop considerations, voltage drop is a reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce the efficiency of the electrical system. The National Electrical Code recommends limiting voltage drop to a certain percentage of the supply voltage, typically 3% for branch circuits and 5% for feeders. Seventhly, when sizing neutral conductors, it is important to consider the impact of voltage drop. A larger conductor size may be required to minimize voltage drop, especially in long runs. Eighthly, different types of buildings have different considerations. The type of building and its occupancy can also influence neutral conductor sizing. For example, in healthcare facilities, the National Electrical Code has specific requirements for the reliability and grounding of electrical systems, which may affect neutral conductor sizing. Ninthly, an understanding of grounding and bonding is also needed. Grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protective devices to trip and clear the fault. Bonding ensures that all metal parts of the electrical system are at the same potential, reducing the risk of electric shock. Tenthly, the National Electrical Code has specific requirements for grounding and bonding, which must be followed when designing and installing electrical systems. 11thly, to summarize, when sizing neutral conductors, it is important to consider all applicable factors, including the type of loads connected, demand factors, harmonic currents, voltage drop, and grounding and bonding requirements. The National Electrical Code provides comprehensive guidance on these topics, which must be followed to ensure the safety and reliability of the electrical system. Understanding the interplay between different sections of the NEC is crucial for accurate and safe electrical installations. Let's examine the connections between sections like 210.19a on, which deals with branch circuit conductor sizing, and 220.6c1, which focuses on feeder and service neutral load calculations. Additionally, we'll explore how these sections relate to Article 310 concerning conductors for general wiring. Firstly, 210.19a on and branch circuit sizing. Section 210.19a on primarily addresses the sizing of branch circuit conductors. It mandates that branch circuit conductors have an ampacity not less than the maximum load to be served. For continuous loads, the conductor ampacity must be at least 125% of the continuous load. This section establishes the foundation for ensuring that branch circuits can safely handle the intended load. Secondly, 220.61 and feeder neutral calculations. Section 220.61 provides the rules for calculating the neutral load of feeders and services. It allows for demand factors to be applied to certain types of loads, such as electric ranges and dryers, which can reduce the calculated neutral load. However, it also requires that the neutral conductor be sized to carry the maximum unbalanced load, which is particularly important in systems with single-phase loads. Thirdly, Article 310 and conductor properties. Article 310 provides detailed information about conductors for general wiring, including their ampacity, insulation types, and installation requirements. It includes tables that list the allowable ampacities of conductors based on their size, insulation, and operating temperature. Article 310 is essential for selecting the appropriate conductors for both branch circuits and feeders. Fourthly, interconnection of all three sections. The interconnection involves understanding that the branch circuit conductors size according to 210.19a on feed into feeders and services. The loads on these branch circuits contribute to the overall load on the feeder, which must be calculated according to 220.61. The conductors for the feeder, including the neutral, are then selected based on the calculated load and the requirements of Article 310. Fifthly, scenarios with nonlinear loads. In scenarios with nonlinear loads, the neutral conductor may carry significant harmonic currents, as previously discussed. In such cases, 220.61 requires that the neutral conductor be sized to carry the maximum unbalanced load, including the harmonic currents. This may necessitate oversizing the neutral conductor compared to the phase conductors. Sixthly, when applying demand factors, it is crucial to carefully consider the type of loads being served and the applicable demand factors. Overzealous application of demand factors can result in an undersized neutral conductor, which can lead to overheating and other problems. Seventhly, conductor ampacity adjustments are used in other scenarios. Article 310 requires that conductor ampacities be adjusted for ambient temperature and the number of conductors in a raceway or cable. These adjustments can significantly reduce the allowable ampacity of conductors, which must be taken into account when selecting the appropriate conductor size. Eighthly, practical examples help illustrate the connection between these sections. Consider a commercial building with a mix of lighting, receptacle, and HVAC loads. The branch circuit conductors for the lighting and receptacle circuits are sized according to 210.19a on. The feeder conductors, including the neutral, are sized according to 220.61, taking into account demand factors and the potential for harmonic currents from electronic devices. The conductors are then selected from Article 310 based on the calculated load and the installation conditions. Ninthly, always refer to the latest NEC edition. It is important to note that the National Electrical Code is updated every 3 years, and the requirements for conductor sizing may change from one edition to the next. Therefore, it is essential to always refer to the latest edition of the National Electrical Code when designing and installing electrical systems. Tenthly, consulting with qualified professionals is paramount. Electrical system design is a complex task that requires a thorough understanding of the National Electrical Code and electrical engineering principles. It is always advisable to consult with qualified electrical engineers and contractors to ensure that the design meets all applicable codes and standards and provides for safe and reliable operation. 11thly, in summary, Sections 210.19a on 220.61 and Article 310 are interconnected and must be considered together when sizing conductors for electrical systems. Understanding the requirements of each section and how they relate to each other is essential for ensuring the safety and reliability of the electrical installation. We can further expand on the practical applications by discussing specific load types and their impact on neutral conductor sizing. Let's consider scenarios involving electric vehicle chargers, LED lighting systems, and data centers. Firstly, electric vehicle EV chargers are becoming increasingly common, and their load characteristics can significantly impact neutral conductor sizing. EV chargers typically draw a continuous load, which means that the branch circuit conductors and feeder conductors must be sized at 125% of the charger's rated current, according to 210.19a on. Secondly, many EV chargers are single-phase, which can create an unbalanced load on the electrical system. This means that the neutral conductor must be sized to carry the maximum unbalanced load, as required by 220.61. In some cases, it may be necessary to install a separate neutral conductor for the EV charger to minimize the impact on the existing electrical system. Thirdly, LED lighting systems have become increasingly popular due to their energy efficiency and long lifespan. However, LED lighting systems can also generate harmonic currents, which could affect neutral conductor sizing. The harmonic current content of LED lighting systems varies depending on the design and quality of the fixtures. It is important to select LED lighting systems with low harmonic distortion to minimize the impact on the neutral conductor. Fourthly, in some cases, it may be necessary to use a neutral conductor that is larger than the phase conductors to accommodate the harmonic currents from LED lighting systems. This is particularly important in large commercial buildings with extensive LED lighting installations. Fifthly, data centers have unique electrical requirements due to their high density of electronic equipment. Data centers typically have a large number of computers, servers, and other electronic devices, which can generate significant harmonic currents. The neutral conductors in data centers must be sized to carry the maximum unbalanced load, including the harmonic currents. Sixthly, it is common practice in data centers to use oversized neutral conductors to minimize voltage drop and improve power quality. Some data centers also use harmonic filters to reduce the harmonic current content of the electrical system. Seventhly, when sizing neutral conductors for specific applications, it is important to consider the load characteristics of the equipment being served. This includes the continuous load rating, the potential for unbalanced loads, and the harmonic current content. Eighthly, consulting with equipment manufacturers and electrical engineers can help ensure that the neutral conductor is properly sized for the application. Ninthly, load diversity and demand factors also have an impact on the sizing. The concept of load diversity can also play a role in neutral conductor sizing. Load diversity refers to the fact that not all loads in the building will be operating at their maximum rated current simultaneously. This can allow for the use of demand factors, as permitted by 220.61, to reduce the calculated neutral load. Tenthly, however, it is important to carefully consider the load diversity when applying demand factors, as overestimating the diversity can result in an undersized neutral conductor. 11thly, to summarize, specific load types such as EV chargers, LED lighting systems, and data centers can have a significant impact on neutral conductor sizing. Understanding the load characteristics of these applications and applying the appropriate code requirements is essential for ensuring the safety and reliability of the electrical system. The selection of appropriate wiring methods and materials plays a critical role in ensuring the safety and longevity of electrical installations. Let's discuss how different wiring methods and materials can affect neutral conductor sizing and overall system performance, taking into account factors like heat dissipation, conductor dating, and environmental conditions. Firstly, conduit systems like rigid metal conduit (RMC), intermediate metal conduit (IMC), and electrical metallic tubing (EMT) offer excellent physical protection for conductors and provide a continuous ground path. However, when multiple conductors are installed in a conduit, the heat generated by the conductors can be trapped, leading to increased conductor temperature and reduced ampacity. Secondly, the National Electrical Code requires that conductor ampacities be derated when more than 3 current-carrying conductors are installed in a conduit. This derating factor must be taken into account when sizing the neutral conductor, especially in systems with high conductor densities. Thirdly, cable systems such as non-metallic sheet cable NM, armored cable AC, and metal-clad cable MC offer more flexibility in installation compared to conduit systems. However, cable systems typically have lower heat dissipation capabilities than conduit systems. This means that conductor ampacities may need to be derated more significantly in cable systems, especially in insulated walls or ceilings. Fourthly, direct burial cables are designed for underground installations and must be resistant to moisture, corrosion, and physical damage. Direct burial cables typically have a higher insulation temperature rating than cables installed in conduit or cable systems. However, the ampacity of direct burial cables may be limited by the soil conditions and the depth of burial. Fifthly, conductor materials like copper and aluminum have different electrical and thermal properties that can affect neutral conductor sizing. Copper has a higher conductivity than aluminum, which means that copper conductors can carry more current for a given size. However, aluminum conductors are lighter and less expensive than copper conductors. Sixthly, the National Electrical Code allows the use of aluminum conductors in certain applications, but it requires that the conductors be sized larger than copper conductors to achieve the same ampacity. Seventhly, insulation types like thermoplastic high heat resistant nylon THHN, cross-linked polyethylene XHHW, and rubber have different temperature ratings and resistance to moisture, chemicals, and abrasion. The insulation type must be selected based on the operating temperature, environmental conditions, and the type of installation. Eighthly, high-temperature insulation allows conductors to operate at higher temperatures, which can increase their ampacity. However, high-temperature insulation may be more expensive than standard insulation types. Ninthly, environmental conditions such as ambient temperature, humidity, and exposure to corrosive substances can affect the performance and lifespan of conductors and wiring systems. In high-temperature environments, conductor ampacities must be derated to prevent overheating. In corrosive environments, conductors and wiring systems must be protected from corrosion using appropriate materials and coatings. Tenthly, when selecting wiring methods and materials, it is important to consider the specific requirements of the installation, including the load characteristics, environmental conditions, and the National Electrical Code requirements. Consulting with qualified electrical engineers and contractors can help ensure that the wiring system is properly designed and installed. 11thly, in summary, the choice of wiring methods and materials can significantly affect neutral conductor sizing and overall system performance. Factors such as heat dissipation, conductor derating, and environmental conditions must be considered to ensure the safety and reliability of the electrical installation. We can further refine our understanding by examining specific code sections related to derating and adjustment factors, particularly 310.15b2 and 310.15b3, and how they impact neutral conductor sizing in various scenarios. We will also touch upon the importance of proper documentation and labeling. Firstly, understanding 310.15b2. Section 310.15b2 of the National Electrical Code addresses the adjustment factors for ambient temperature. This section requires that conductor ampacities be adjusted downward when the ambient temperature exceeds the temperature rating of the conductor insulation. The adjustment factors are provided in tables in the National Electrical Code and vary depending on the insulation type and the ambient temperature. Secondly, understanding 310.15b3, Section 310.15b3 addresses the adjustment factors for the number of current carrying conductors in a raceway or cable. This section requires that conductor ampacities be adjusted downward when more than 3 current-carrying conductors are installed in a raceway or cable. The adjustment factors are provided in tables in the National Electrical Code and vary depending on the number of conductors. Thirdly, applying adjustment factors is crucial when sizing neutral conductors, especially in situations where the ambient temperature is high or there are multiple current-carrying conductors in a raceway or cable. Failure to apply the adjustment factors can result in an undersized neutral conductor, which can lead to overheating and other problems. Fourthly, scenarios with high ambient temperatures. In high-temperature environments, such as industrial facilities or attics, the ambient temperature can significantly exceed the temperature rated of the conductor insulation. In such cases, the adjustment factors in 310.15b2 must be applied to reduce the allowable ampacity of the conductors, including the neutral conductor. Fifthly, multiple conductors in a raceway. When multiple current-carrying conductors are installed in a raceway, the heat generated by the conductors can raise the temperature inside the raceway. This can reduce the allowable ampacity of the conductors, including the neutral conductor. The adjustment factors in 310.15b3 must be applied to account for this effect. Sixthly, neutral is a current-carrying conductor. In some cases, the neutral conductor may be considered a current-carrying conductor, which can affect the adjustment factors that must be applied. For example, if the neutral conductor carries a significant amount of harmonic current, it may be considered a current-carrying conductor for the purposes of applying the adjustment factors in 310.15b3. Seventhly, proper documentation and labeling are essential for ensuring that electrical systems are properly installed and maintained. The National Electrical Code requires that electrical panels and equipment be clearly labeled to indicate the voltage, amperage, and other important information. It is also important to document the conductor sizes, wiring methods, and dating factors that were used in the installation. Eighthly, accurate documentation helps ensure that future modifications or repairs can be performed safely and efficiently. It also helps prevent overloading of the electrical system, which can lead to fires and other hazards. Ninthly, code compliance and inspections are essential for ensuring that electrical installations meet the requirements of the National Electrical Code and other applicable codes and standards. Electrical inspections are typically performed by local building officials or third-party inspection agencies. Tenthly, electrical inspections help identify potential safety hazards and ensure that the electrical system is properly installed and maintained. 11thly, to summarize, understanding and applying the dating and adjustment factors in 310.15b2 and 310.15b3 is crucial for properly sizing neutral conductors and ensuring the safety and reliability of electrical installations. Proper documentation and labeling are also essential for maintaining the electrical system and preventing future problems. Finally, it's important to emphasize the role of ongoing education and training in staying current with the ever-evolving electrical codes and best practices. Here's a look at resources for professional development, the significance of field experience, and the importance of adhering to manufacturers' instructions. Firstly, continuing education is crucial. The electrical industry is constantly evolving, with new technologies and code updates being introduced regularly. Continuing education courses, seminars, and workshops provide electricians and electrical engineers with the opportunity to stay current with the latest developments and best practices. Secondly, resources for professional development. Numerous organizations offer professional development resources for electrical professionals. These include the National Fire Protection Association, the Institute of Electrical and Electronics Engineers, and various trade associations. These organizations offer courses, certifications, and other resources that can help electrical professionals advance their careers. Thirdly, certification and licensing are important considerations. Many jurisdictions require electricians and electrical engineers to be licensed or certified. Licensing and certification demonstrate that an individual has met certain minimum qualifications and has the knowledge and skills necessary to perform electrical work safely and effectively. Fourthly, field experience is invaluable. While classroom learning is important, field experience is essential for developing the practical skills and knowledge needed to excel in the electrical industry. Working alongside experienced electricians and electrical engineers provides opportunities to learn from their expertise and gain hands-on experience. Fifthly, mentorship programs can be very beneficial. Mentorship programs can provide valuable guidance and support for those new to the electrical industry. Mentors can share their knowledge and experience, provide advice on career development, and help mentees navigate the challenges of the industry. Sixthly, adhering to manufacturers' instructions is critical. Electrical equipment and components must be installed and used in accordance with the manufacturer's instructions. Failure to follow the manufacturer's instructions can result in equipment malfunction, safety hazards, and voiding of warranties. Seventhly, understanding equipment specifications. Electricians and electrical engineers must carefully review the equipment specifications and installation instructions before installing any electrical equipment. This includes understanding the voltage, amperage, and other ratings of the equipment, as well as any specific requirements for wiring, grounding, and bonding. Eighthly, safety protocols must be followed. Safety should always be the top priority in any electrical work. The electricians and electrical engineers must follow all applicable safety protocols, including wearing appropriate personal protective equipment, using insulated tools, and energizing circuits before working on them. Ninthly, regular safety audits can ensure proper protocol. Regular safety audits can help identify potential hazards and ensure that safety protocols are being followed consistently. Safety audits should be conducted by qualified personnel and should include a review of work practices, equipment maintenance, and safety training programs. Tenthly, staying informed about industry trends is important for long-term success. The electrical industry is constantly evolving, and it is important to stay informed about the latest trends and technologies. This can involve reading industry publications, attending conferences, and participating in online forums. 11thly, in summary, ongoing education and training, field experience, and adherence to manufacturers' instructions are all essential for ensuring the safety and reliability of electrical installations. By investing in professional development and staying current with industry best practices, electrical professionals can provide high-quality services and protect the public from electrical hazards.